Welcome to the Road to Research seminar series. Thank you so much for joining us today. I'm Jennifer Ravelli. I'm the Assistant Dean in the College of Science and Mathematics. And before we get started, I want to encourage you to post your questions to the chat box. And after we finish the presentation, we'll be answering your questions. So with no further ado, I'd like to introduce to you Dr. Eduardo Flores. Dr. Flores is an associate professor in the Department of Physics and Astronomy who's been with Rowan University for over 30 years. His research focuses on the paradoxes of quantum physics, and he's here today to talk to us about that. Welcome, Dr. Flores.
Thank you. Thank you. Okay, thank you so much for inviting me, and let's just get started. So how did I ended up doing research? Well, let's see a little bit of my story. All right, so when I was very little, I like to take everything apart. My parents' clocks, toys, everything, nothing was safe. My parents had to start locking things from me. I was very young. I just like to see what things are made of, how they work. And I remember I was given a plane at some point, a little airplane to play. And then I took it apart. Obviously, it took in 2 days. And then I found this thing and I said, this must be what moves the plane. But how does it run? I don't know, I was 3, 4, something really young, maybe 5, I'm not sure. So I took this little thing and went to my mom's drugstore. She's a pharmacist. And let me see, it was going by. Okay, but this way. Okay, and I found a battery and I connected those 2 pieces of the wire to the battery and the thing ran. I was totally amazed. I was like so happy. So, and then my life continued. I was a very regular child. I didn't like school. I struggled. My sister, my older sister, she was the brightest student, valedictorian. All my sisters were really good. I struggled big time. When I was about, I mean, you know, I have 2 brothers and 3 sisters. When I was about 6th grade or so, I had a teacher who kind of started encouraging me. And I was like, why is he paying attention to me? And it was very helpful. I started doing better in school, but still I was just a regular kid who didn't like school. And I was doing it because my parents made me do it. I was going to very good schools though. So I'm so bad I didn't take more advantage of that in the early days in Ecuador. Well, but I went through high school. That was story too, but nothing special. I didn't know what I wanted to do. I just was a little bit lost, but I wanted to make my dad happy. He was an architect. He had a construction company and he wanted me to become an engineer, probably to join his company. But okay, so I enrolled in engineering and I saw the number of courses engineers had and their schedule was packed every day from 8 a.m. to 5 p.m. I said, I cannot do this. I got trouble with the school. It's gonna be the end of me. So I changed major. I look at the math schedule. Math has lots of free times. So I say, I want to be a math major. So as a math major, I had some very good teachers. And one of them asked me to write, asked all of us to write an essay on why do I want to be a math major. And my essay essentially said that I want to be a math major because math will unveil to me the universe and how it works. And my teacher said, yeah, I you know, math can help you, but that's not what math is about. All right, so yeah, maybe I'm the wrong place. So I guess I went back to engineering myself. So And also I came to the US. I wasn't doing very well in school. My dad, I was begging my dad that I want to go somewhere else. And he eventually said, okay, he got some relatives here. So he sent me to the university here in the US. And in my first semester in engineering school at New York Tech, I realized I really do not like engineering either. I mean, I had excellent teachers at New York Tech, and especially my math teacher. Um, I, I, start, I started to want to do something well. I wanted to be a good student at least. You know, my parents have been so patient with me and my bad grades throughout my life. So I just wanted to pay back by doing well in school. So, and I was doing okay. Um, since I had a very good high school and elementary school in Ecuador, um, college wasn't that hard for me here in the US. And actually my math teacher, Dr. Vitale, introduced me to um, other teachers, and he said, he's my brilliant student. I was like, what? This in Ecuador, you don't even dream this to happen to me because the environment is different. It's like teachers are way above students, and they wouldn't say of a student like that unless it's a super brilliant. But I wasn't super brilliant. I was just pretty much a regular student. Actually, sometimes less than irregular. But also, I had another physics teacher there, New York Tech, and he said, "You're good in physics." Yeah, I was taking physics 2 with him, and he liked what I did, and he encouraged me. And I told him, but my dad doesn't want me to be a physics major. He said, well, do what your parents tell you. They know why. Okay. I went back to Ecuador in the summer, and I told my dad that I want to be a physics major. And he was like, what? I thought you were going to be an engineer. I said, no, Dad. Well, he said, son, whatever you do, do the best you can. Yes, I became a physics major. And then really, I became a physics major due to Einstein's influence. Once in New York, I was walking, I entered a used bookstore, and I found a book for the layman, not a specialized book. It's just for the regular person by Einstein. The book talked about relativity of space and time. In the book, I found that the attractive effect of gravity between, let's say, the Earth and the Sun, the Earth and the Moon, is due to a bending of the structure of a space-time. This was an amazing thing to me, just thinking of that kind of thing can happen. So I wanted to learn more about it. That's how I decided to become a physics major, plus the encouragement of my teachers. So for instance, if this is the Earth, a satellite is going round and round the Earth, not because there is a force between the Earth and the satellite, but because the space, empty space that looks like nothing is there is actually not a straight or flat, and nothingness is actually a structure. And the satellite feels like it's going in a straight line in free fall, but really is turning because the space happens to be curved, bent. So that was so interesting to me. So and many of the Einstein quotes became inspiration. I remember one of them says, Einstein said, gravitation cannot be held responsible for people falling in love, because of falling. His views on February 14th. But yeah, his theory of general relativity is a theory of a space and time that is a structure that is dynamical, that can change and bend. Based on simple observations, like, when you are in a car, you accelerate, the feeling you get is identical to the effect of gravity. That's the basis of this theory, where it builds from. It has a mathematical tool called tensors. So I remember in first year of graduate school, after the first year, I took my summer off just to learn this theory. That's how much I liked it. Until I had no more money. And then I had to go to an experimentalist and said, could you give me a work, some job? I have no money. So yeah, one thing that Einstein said is the most incomprehensible thing about the world is that it's comprehensible. Yeah, this really summarizes the science in the Western world, um, that we can understand the universe. Okay, so that there is a reason behind things. So it is the philosophy of a way of thinking that really drives you when there is no other light. And this is actually something I have faced too. It's so amazing that we could actually understand our universe. It wasn't true for all civilizations. In most civilizations, people thought that at the end of, because they studied too, they discover things, but they thought there is a limit and then there is chaos at which nobody can understand anything. And that's really the end of the civilization, the end of science. So I have myself been faced to that point when beyond this, it seems like it's chaos, cannot be understood. But this drive, this philosophy about the universe has really made big time effects. That's why the Western world developed so much. Like, people playing with magnets, electricity, currents, Faraday, Coulomb, Gauss, Ampere, others, ended up um, in the equations that Maxwell put together at the end in 1861, called Maxwell's equations. And this theory predicted that light was a wave made of electricity and electric and magnetic fields. So yeah, so it was quite amazing. But this went on for many years. 25 years later, a guy named Hertz started working on these waves predicted by Maxwell. And between the years 1885 and 1889, he discovered what is called electromagnetic waves. But he didn't realize the importance of this. He just did because he loved it. Okay. Actually, he was given a press conference because something was interesting about it. At the press conference, they asked him, what have you done? He says, oh, it's not used whatsoever. This is just an experiment that proves that Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. He was asked, what could you do with it? He replied, nothing, I guess. So he was a true scientist in the sense he was just studying for the sake of it, not even thinking of what to apply, but just so interesting that you had to keep going. So that's another quote of Einstein. The important thing is not to stop questioning. Curiosity has its own reasons for existence. Yes, you keep asking questions. And Einstein too did not quite like this theory of quantum mechanics because he saw that there is a point that it seems like it breaks with common sense, it breaks with rationality. So one of his quotes is, as I have said before many times, God doesn't play with dice with the world, because quantum mechanics brings a randomness to the world. So, and quantum mechanics has outstanding problems. This theory of Einstein and the theory of particle physics, quantum mechanics, are not compatible. There is something called dark matter that we see around galaxies, especially, and we cannot see what it is. Nothing that we have seen before is like it. There is also a prediction of dark energy, which is in great abundance, which also we do not really know the origin of it. And in quantum mechanics, there is some spooky actions at a distance. Something here could affect something in London in faster than the speed of light can travel from here to London. So those kind of things have been actually measured. And so it's a world that is quite mysterious. And there is these tiny particles, photons for light, electrons for matter, protons, and they are like little dots of energy. Yet there is also a wave attached to them. So a lot of mysteries in this world. So when I was an undergraduate, I was at New York Polytechnic, which is now part of NYU Engineering. And that's what I did my undergraduate. And I wanted to do research. So I went to a faculty member who used to take graduate students. And I asked him, I want to do research. Well, he took me the first semester, asked me to understand something for him in quantum mechanics. I hadn't had quantum mechanics yet. So I studied. I just had a hard time helping him. So, but the second semester came and I said, I want to continue doing research with you. I really want to understand something. And he said, okay, now I'm not going to tell you what problem to work. I just go find yourself and make sure it's good. So I went to Richard Feynman's lectures in quantum mechanics, and it was pretty amazing. He's very, very clear. These lectures were for like first, second year students at Berkeley, I think, where he was, or Caltech, one of the, oops, forgot. So what is his challenge? Well, it was something like this.
In this film, we're concerned the interference patterns of ripples made on the surface of water. The ripples are produced in a ripple tank by two dippers which vibrate on the surface. Light passing through the water is reflected from a mirror through a lens to form an image of ripples on a screen. We've obtained this true image by the Schlieren technique of inserting a stop in the light path. The two small dippers vibrate on the surface of the water. Each dipper produces its own pattern of ripples, and the two sets of patterns overlap. In step, they produce a pattern like this. Out of step, they're vibrating in antiphase and produce a different pattern like this. So that we can study these patterns more closely, the images formed by the ripples have been slowed to 1/24th of their actual speed by stroboscopic means. Two sources are here vibrating in phase, producing crests and troughs in step with one another. The result is an interference pattern. Along these lines, the waves from the two sources always arrive out of step and neutralize each other, producing interference fringes of minimum wave motion. Minimum wave motion, maximum wave motion.
Let's go back. So most people have seen, if you have water in a tank, you just touch the water, you see little waves. And if you have two sources, you see these nice patterns called interference. So this is with any kind of wave. You can do it with sound, with water waves, et cetera, et cetera. So what's interesting about it? Well, what's interesting about it is that you could also do this with actual electrons, little dots, little particles. So you made them go through two openings, okay? In this opening, is like one source, a second source, like to make ripples. And guess what? You get identical pattern as with the waves of ripples. And this is done by matter, by little dots. And this is formed very slowly. You could have one dot at a time. You could do also with light, you get that. And this is, if you do it, you could do one electron at a time or one photon at a time. And this is what you will see. These wave patterns are built one dot at a time. So if you could do it so slow that there is, at a given time, there is only one dot and then second dot. And eventually this is formed. So this is quite mysterious. So this was the Feynman challenge. How could matter do that if there are little dots? How could there be dots that make waves? So this is the challenge I found when I was asked to do my research project. So my quest was to solve this problem. In my research for an undergraduate course, I wrote a paper. So eventually at the end of the semester, I wrote a paper explaining how, my solution to this problem is. And I said, must be something in a space, must be a structure of a space. And the structure of a space is that propagates as a wave. These waves tell electrons where to go and where not to go. And this is how the patterns are formed. It turns out that the structure of a space does vibrate and does propagate at waves, but these are called gravitational waves, which we just discovered a few years ago. So, well, then I went to graduate school at Michigan. It was a great place, nice people, lots of freedom, lots of freedom, lots of snow too. And the teachers were great. For instance, one of my teachers, one of the inspiration teachers, besides my PhD professor too, who Dr. Yao, but this professor, Dr. Bellman, was interesting. If you go to his lectures, he will just talk. He will just talk to you, hardly write. Once in a while, he'll write something, but he just talk. It was very interesting. I love going to his lectures, but it was just like, time to watch TV, kind of relaxing. The amazing thing is that when I was doing my graduate work, all these things that this teacher said became a little light for my path in my research. And I was amazed how his insight and his talk was illuminating my path of research. So once in a while, you find these amazing people. By the way, he, in few years ago, 20 years ago, he got a Nobel Prize. Without him, we wouldn't have particle physics the way we have now. So it was pretty amazing what he did. And his student. So in physics, we do have problems, especially trying to solve this wave particle problem. So the standard understanding of the problems of this wave and particle problem is called the Copenhagen interpretation. According to the Copenhagen interpretation, we should not say that particles are like a point or like a wave. In fact, they are neither. So according to this interpretation, which is the standard interpretation of quantum mechanics, things only make sense once detected, once you see them. So in reality, then this approach really goes against the existence of a physical reality outside our consciousness. So this is what actually you have to end up thinking if you just take all the facts of quantum mechanics and try to make sense with them. You end up thinking this way. I was going the same direction too at some point, until I had a philosopher of science at Princeton. When he lived in Princeton, he wasn't from Princeton, but and he talked to me, and I explained to him that I started to believe this, and he just shook a little sense of me. He said, this denies reality. So I decided I want to solve this particle duality problem. And as I said, I thought maybe like, the particles move in space, and the space changes the structure, and that is how the particles, the waves show up. But I found out that it's a structure of a space is way too strong to generate any kind of motion by a tiny particle. So, and also these waves are almost like without energy. Most of the energy is in these little particles. But people have been working for like nearly 100 years on this problem, and they haven't gone very far. So at some point, this work has been stopped. on understanding the wave-particle duality. So many journals do not want to entertain papers on the subject. They just see it and say no. Or I called NSF once some years ago, and I talked to them about when I work on this problem, and they told me, "We're sorry, but there is no grant money or no published papers, no promotions in this kind of field. You have to do something different." Well, what to do? I could have joined lots of problems were interesting, very interesting, popular, and would produce papers, would produce promotions, grants. However, I did not come to physics to get rich. That was what I thought. To me, it was more important to discover something than to get ahead with, in my profession, really. But I really want to discover something. That's more of a driving force. So I decided I'm not going to worry about it. Fortunately, I have a tenure, so I'm going to work on this. So what will I do is I will study and will teach, two things I love. So I'm still a student. So I study and teach, do research and teach. And guess what? I think I got a solution. Now, just because I think I got a solution doesn't mean that people agree that I have a solution. I just, when Einstein realized that light is made of little particles called the photon, even though he had already introduced relativity, which was an outstanding thing, it took him 20 years for the community to accept this idea that light is made of little dots of energy called the photon. So just because I have an solution doesn't mean, the people are going to accept it. So I have to work on every detail of this theory. I have to make it understandable, take the mysteries away, make it rational, something you could understand. And so this has been a very, very long and hard work. And fortunately, I've been able to solve most of the problems. But, so essentially, the solution goes that particles like electrons, photons of light, and every other particle is, including molecules, a particle, and there is a wave to it. So the particle is the carrier of energy momentum. What is the wave? Well, the environment, the space surrounding the particle is dynamical. As the structure is dynamical, and we know because gravitational waves, but also there is an internal structure to it that it changes. So this wave effect is really an internal structure of a space that affects how particles do and what particles do. And these changes are propagated as waves. So the particle and its environment are strongly correlated. This is the essence of the wave-particle duality. So, and along the way, I have had related surprises, like maybe 3 years ago, a group of students and I, we were working on a project thinking of a structure of a space that might be discrete. So we calculated something in field theory, and we found a value, correct value. You see, this theory called field theory is a wonderful theory, but it's filled with infinities. And whenever you get some answer, you have to get a fish out of the infinite numbers. You have to pull something finite, and that's really tough sometimes. So we found a way to do it without having to do this. Directly we get the answer, and the correct answer. This effect is called the Casimir force. It's force between two mirrors in vacuum. In the absence of everything, particles tend to collapse. They're attracted to each other. And we are able to find this force by simply assuming that space is not a continuous thing, but it's a structure like a lattice. And we got it. So this paper is in is in the process of being accepted. So we're just doing the last few touch-ups with the editor responded to us and some changes. So, but this is amazing because this work was really motivated by undergraduate students and coming to me and wanting to work on a problem. I'm finding a problem related to what I know, space, time, wave particle duality, and then work together, not know where we're going, and eventually finding something. It's not quick, it's not easy, it's very satisfying at some point, and it's fun. I enjoy seeing those students in the summer working in summer research at Rowan, doing the calculations, get very excited, and they have been my driving force in that sense, yes. So I say a big thank you. Who I thanks? Well, I thanks Rowan. Students and faculty have been a great help. Much of the success of my work, as I said, I think I have a great solution. It has been by the feedback from faculty, talking to them sometimes, as students asking questions, or yeah. So being a Rowan has been crucial. I don't think this kind of work I would have been able to do at school, which is more teaching oriented or more research oriented, because if it's research oriented, I would have had to produce grants and money all the time and not be able to work on something fundamental that there is no money for it. So it's been great. Thank you to the Dean Office for facilitating this presentation. In particular, Jennifer Rovelli, who I just met yeah, through the camera today. And thank you for your attention. So feel free to ask questions and also emails. So I'm just opening now for questions. So let me see what we have.
Yes, so please, I'd like to thank you so much for sharing your story with us, Dr. Flores. It was amazing. Your commitment to curiosity is just so liberating, as Bridget Malone posted. Please, everyone, ask us some questions in the chat box, but we do have a few questions for you.
Sure.
So do you think your trouble in school changed because you were doing what you liked, or did it change because you decided to work harder at it, or what was that change?
All right. When I was in elementary school and high school, I was not that interested in school. Probably I thought my sisters are too smart to catch up with them. They would just get the best grades, and I didn't. And I tried hard, so I just kind of gave up for a while. Maybe, there is some problems I have. Maybe I was a little bit dyslexic and I had trouble reading and comprehending. So those kind of things, made it difficult for me, that even when I was trying. So sometimes when I was trying, I just gave up because, a lot of my classmates were brilliant. My sisters were brilliant. And here I was, But once I had in 6th grade a teacher who saw something in me and he started encouraging me, I went from the bottom of the class to near the top. So that was amazing to me. So I think I respond to encouragement. And then in graduate school, my teacher saying, thinking that I was a good student that was here in the US, it was amazing. I think teachers seeing something in you and trying to help you or push you or encourage you is been key for me to yeah.
And so did your experience with your teachers and instructors in Ecuador change the way you interact with students now?
I think so. In Ecuador follow a European style teacher is way above the student. And obviously that kept me a little afraid of them, a little far. Here in the US, there is, I feel, much more freedom in this area, and that is good, healthy for everybody. And teachers talking to you like, like a regular person was very good, and also encouraging you. So yeah, so I remember sometimes when that happened. So teachers were in Ecuador were a little bit like elite. So now I interact with the students. I try to make them feel like like me. I'm not special. I'm just ahead of you.
That's great. So given that, how did you decide to go to graduate school as opposed to going out into a career? And how did you decide on Michigan?
Okay, so as an undergraduate, I took this independent study on research, probably because some other students were doing the same thing. It wasn't mandatory. And finding this problem, this challenge by Richard Feynman on the way particle duality was key. The moment I was given that problem, I found that problem myself. I said, I want to solve it. I want to solve it. And then the natural thing was to go on to graduate school to work on it.
Did you have a mentor that helped you get into graduate school, or did you have to figure that out on your own? What was that process?
Yeah, I when I was in New York, New York Polytech, it was a small physics department, and the teachers were very nice. They were just telling us, apply here, apply there. Yeah, they were encouraging. They were, yeah, the fact that we could get close access to teachers there was very positive thing. And we tried this at Rowan too. We tried to work very closely with the students, and we help them that way too. So
that's great. And what advice would you give to a student who's considering changing majors? Or similarly, what about a student who can't decide on a major?
I would say this, looking at my own life, there is something in you that is special, and you may hopefully know a little bit what it is, or or you can discover through the things you actually do and like I realize now, looking back, that when I was very little, I wanted to know why, what, how. So I broke everything apart. And then I went through all my elementary and high school not knowing what I'm going to do. But already this thing was already in me, that I really wanted to discover the universe. I just didn't know myself that I wanted to do that. I wanted to. So there is something in you already that you could look inside deep and see, this is what I like to do. And yes, may not be popular, but I think I could do something here. Or you may think, I might not be able, I may not be good enough for this. That is, I mean, if I have compare myself with my classmates, and especially in Ecuador, I had such a brilliant group of classmates. It's like they seemed like they were genius in many ways, because I was going to a very good school though. So I would think I'm definitely not good enough like they are. But yet, I think being able to do the research I'm doing and try to solve and work on the problems I have it's been outstanding. So it's not being just my abilities that needed to be good enough. It's been more my interest, my desire, my curiosity, and not giving up.
And we have a student ask, what was your motivation to attempt to solve hard problems rather than advance your career in a field that maybe was more profitable? I mean, you talked about you didn't have any money, and it's a big decision, right?
Right. Yeah. I remember my even when I was at Michigan, the typical thing, the popular thing was to study string theories. And two of my big teachers, Ballman and Yao, who was my thesis advisor, they didn't like string theories. They thought there was not real physics in it, but I knew that that was the thing that people should do. So my advisor asked me, Eduardo, he said, I think you should go into that field, because in the present field you are in, just in field theory, you'll be a scam. You will be nobody. I thought myself, yeah, but I like it, and this is what I want to do. And he said, okay. So I think it was. I think if I find something that I think is important, I do not worry so much. That may not be in the main wave of things to do, because things keep changing. And I did try for a while string theories, by the way, and I just I didn't see interesting things there. Mathematically very complex and very amazing from the mathematics, but I didn't see physics in it. So yes, I had to make a choice, knowing that my choice will imply things like, knowing that this kind of field will not be as rewarded monetarily as other fields, but knowing that I am not in it for the money. But of course I need money, but not that much money. So.
Great. So how did you decide to really tackle your research? Did you hit any walls? Did you have barriers?
Right. Yeah. So most of the time, when you're doing research, you do hit lots of barriers, lots of walls. But I think the thing is to have the problem in your head, because many times you are actually sleeping or doing something else or playing, and some of those problems that you had get solved in your head, because your brain doesn't really give up on working on something just because you don't see a solution. Your brain continues working on it. Actually, amazing things have been found that way. Like, people have put their problems in their heads, and then later on, when doing something random, they realize of something. So yeah, you hit walls in every field, but work on them for a while, and just put them aside. And then guess what? You will see a solution somewhere, or somebody will tell you something, or you will find it. The thing is not to give up, though. If you really want to work on this, you can give up working on it right now, but you could not give up on your idea that you want to do.
That's great. So what was the differences being an undergrad in New York and a grad student in Michigan?
Oh yeah, that was like going from, I'm sorry to say, but it was like going from hell to heaven. In New York, I felt like I out of place, because I felt it was a business place. People in a rush. People don't talk. People running. Everybody in suits. It was sneakers, jeans. So I felt like out of place. And then when I arrived to Michigan, everybody like me, all the stores were run by students. Everybody is smiling, no rushing, talking, being nice. I said, wow, is this real? So, and at the level of science too, I mean, the university in New York was nice, a little place, but outside that, it was a different world. But at Michigan, everywhere was nice, similar, friendly. I think friendly is the word.
Wow. And I can imagine it must have been challenging to go from Ecuador to Michigan and all that snow. How did you acclimate?
Actually, I come from Ecuador in a mountain region where it's actually cold. It's not that cold, but it's so actually I do better in cold weather than hot weather. So so that wasn't a problem. But I remember my first year in Vermont, my first really cold weather. I don't know if you've seen snakes, but the snakes lose their skin. I lost my skin too. Suddenly, my skin was peeling everywhere in my body.
Oh.
Yeah, but it was good after that.
Okay.
It was just funny.
And can you tell us how you got from Michigan to Rowan?
So
What the path was?
yeah, so I wanted to really, my idea was after Michigan to become a peer researcher. I had no really inclinations of doing teaching. However, I kind of knew what I wanted to study. And in my interviews for postdoctor to continue research, they were honest and they would say, what problem do you really want to work on? And I will tell them my problem. I want to work on relativity and things like that they're not that popular. So I didn't get those kind of jobs because I had an idea what I want to study. So the available thing was teaching jobs. So I got a temporary 1-year teaching job in Indiana State University, just teaching physics. And then after that, I applied to Rowan and I got a tenure track position. So yeah, I applied many places, but Rowan said yes, so I just came.
Well, lucky us.
Yeah, well, lucky me too.
So are there other subjects that you research besides wave particle paradoxes?
Well, in physics, yes. I'm very interested in relativity, gravitational waves, structure of space and time. Yeah. And yes.
Lots of stuff, it sounds like.
Right.
Well, that's great. So we're coming to the end of our time. If anybody has any more questions, we do have a question about when you go back home to a sea level of 7,000 feet, how long does it take you to get acclimated to no air when you come back?
Yeah. Actually, when I go from sea level to actually is probably is about 12,000 feet, Quito. So you come out of the plane and your heart beats fast. And then you go up the stairs and you're out of breath. You only have 70% of the oxygen.
Wow.
So you run at 70%. And your body takes time to produce more red blood cells to compensate. Eventually you get the red blood cells compensate after a month or so. And then you come back to sea level. And now you have too much energy because you have too much oxygen. But it regulates itself in a little while. So it's kind of good.
So that's how you get all that research done, right?
Yeah, exactly.
Okay. So my other question is, what is your favorite thing about being a teacher?
I think I love to be able to give a good, clear, sensible explanation so that the students feel that whatever they are listening, it makes sense to them. That's what I like best, that being able to reach them, to make sense to to them. When that doesn't happen, I feel depressed. But when I feel like I'm giving them something that is good for them and makes sense to them, I feel great.
Sorry. So in the next couple of years, what do you think science will discover? What direction is science heading?
Wow, that's
a big one.
That's a big one.
Yeah.
So I think in physics itself, probably is going to be quite a bit of work on these quantum computers, because the possibilities that they do so much faster, so much better calculations is such an interesting thing and good thing. Because even though computers are good and fast nowadays, for instance, for some of my calculations, they take a long time. So, and I imagine when complex problems, sometimes we don't know how to handle them because the computers cannot handle them. So yeah, I think in physics, quantum computing will be a big thing. I wouldn't venture to say medicine because I don't know much about it. I know some, but not much. But yeah, quantum computing is going to be big in physics.
And then finally, can you tell us a little bit, what do you think about students doing undergraduate research?
I think that's how I got into research. And I think the students who I had, we had as in research, it just turns 180 degrees. It goes from being a spectator to being a player. And that is a big difference. You know, you could watch every concert, music, piano, watch somebody play the piano for years and years and years. But unless you go and sit on the piano and try it, you will never be able to play the piano. So same is in physics. So it really makes a big difference. Some schools is required almost, or yeah.
Thank you. So on that note, I think that if you have any more questions, please send them to the chat box. I think we've come to the end of our questions, but I really, really appreciate your time. So I have one that says that Brian Greene suggests that in his latest book, we don't have free will. Everything's driven by the law of physics. What are your thoughts on that?
I would say from the biological point of view, he's almost right. There is some quantum mechanics has in its essence something that is a little bit unpredictable. So even from the scientific point of view, I have doubts you could actually make that statement. You could almost make it, but not quite, because even quantum physicists tell us there is something is non-deterministic. But really, to be honest, free will is something human and is practically beyond physical. But yeah, I believe we have free will.
All right. Well, thank you for taking the time to meet with us today and share your story. It was fascinating. Again, your commitment to curiosity, I think, is what really, it was what I took away from this talk, is that you keep working, you keep trying, and you follow your interests and your curiosity. I would like to invite everyone, thank everyone for joining us. We're going to pop in the chat box, and our next Road to Research is May 19th. Please join us for that one. And thanks for taking the time today. And thank you so much, Dr. Flores.
Thank you for inviting me. And thank you for the students who came. And so great.
All right, everyone, have a great Friday. And thank you again for joining us. Take care.
Thank you, Professor Flores.
Thank you, Dr. Flores.
Welcome.
Thank you so much.
Thank you, Dr. Flores. Take care.
Thank you.